Hello everyone, I'm Norman Wildberger. Today we're going to be looking at systems of linear equations, which is sort of the heart in some sense of linear algebra, solving linear equations, but not just one of them, several of them, and not just one variable, but several variables. Okay, so that's the challenge. Okay, so here is the xy plane, and we have two lines. One of them is given by the equation x plus 2y equals 2, and the other one is 3x minus y equals 3. And what we want to do is we want to find this common point of intersection, or the meet of these two lines. And that, of course, is finding the point xy that satisfies both the equations. Okay, so what we're going to do is we're going to sort of eliminate one of the variables and find the other variable, and then we'll substitute that back into one of the equations to get the first variable. Okay, so let's call these equations something. Let's call this one number 1 and this one number 2, let's say. And then what we're going to do is we're going to take some combination of them so that the total x's that we get is 0. So we're going to eliminate x. Okay. So maybe I'll say that once here. So we're going to eliminate x. How do we do that? We're going to take the combination. We're going to take the equation 2 and subtract 3 times the equation 1. So we're going to have 3x minus x. So we're going to get 0 x's when we do that. And how many y's are we going to get? So there's minus y from equation 2. And then we're going to subtract 3 times equation 1, so subtracting 3 times 2 for a total of minus 7y. And on the right hand side we have 3, I'll write that down, 3 minus 3 times 2. Okay, so altogether that's the equation. Minus 7y equals 3 minus 6 is minus 3, so y equals 3 over 7. And then what we do is we can substitute that back in, maybe go up here. So therefore, x plus 2 times 3 over 7 equals 2. And that's like x equals 2 minus 6 sevenths, which is altogether 8 sevenths. Okay, so we get that x is equal to 8 sevenths. So this point here, we've now found its coordinates. The x coordinate is 8 over 7, and the y coordinate is 3 over 7. And in this case, there's a unique solution. This is the only solution. So maybe I'm up here. This is the case of having a unique solution. There's only one point which lies on both lines. All right, so now let's scroll to a next example. Here we have two lines. One of them is given by the equation 2x plus 3y equals 6. And the other one is given by 4x plus 6y equals 16. Now, I've graphed these lines for you, and they appear to be parallel. Okay? In fact, they are parallel because the normals we can read off from the equations of the lines pretty easily. So a normal to the first line is the vector 2, 3. And a normal to the second line would be the vector 4, 6. Right, that's how we get the normal from the equation. We look at the coefficients of x and y. Coefficients of x and y. And these two vectors, 2, 3, and 4, 6, are multiples of each other. They're parallel, and so these lines themselves are going to be parallel. So that tells us that we are unlikely to find a joint solution to both of these lines. We are not going to find a point x, y, which lies on both the lines. But let's try anyway. So we'll call this one 1, and we'll call this one 2, and we'll go through the same procedure that we did before. So let's take equation 2 and subtract 2 times equation 1 to eliminate the x's. Okay, that's our idea. Okay, what happens? Well, we get 4x minus 2 times 2x, so that's 0x. How many y's? There's 6y minus 2 times 3y, so I guess that's 0y. And 16 minus 2 times 6 is 4. Now, 0x plus 0y equals 4. That's a relatively simple equation because it's really the equation 0 equals 4. And there's no solutions to that. It doesn't matter what you plug in for x and y, there's no solution. So that's the answer here. There's simply no solution. There's no common intersection or meet of these two lines. Now, third example, we have two equations, but actually the lines geometrically look very similar. So the equations are 2x minus y equals minus 2 and 6x minus 3y equals minus 6. So maybe we didn't know. We haven't looked at that. We don't know that they actually overlap because we haven't gone through the trouble of drawing a diagram. If we just work algebraically, how can we tell, what's going to happen? So let's do the same thing that we did before. We'll label them, say equation 1 and equation 2, and then we'll try to eliminate, let's say, the x's. Okay, so how are we going to do that? We'll take equation 2 and subtract 3 times equation 1. So equation 2 minus 3 times equation 1. And what does that give us? Well, 6x minus 3 times 2x, so it's going to be 0x. And then the 3 minus 3y minus 3 times minus 1, so that's plus 3y, so it'll be plus 0y equals minus 6 minus 3 times minus 2, so it's minus 6 plus 6, that's equal to 0. Okay. What we're seeing there is that the difference between these two equations is really 0. That's sort of what that's telling us. These are the same equations. So what are the solutions to this joint pair of equations? Well, it's just all the points lying on the line. So there's, in this case, an unbounded number of solutions. You can cook up as many as you want. Number of solutions. So any point on, say, just equation 2x minus y equals minus 2. And how could we actually sort of describe points like that? Well, one way would be to set, let's do it here. Let's set one of the variables, let's say y equals to a parameter, let's say lambda. Okay? Then the equation would become 2x minus lambda equals minus 2, so that x will be lambda minus 2 all over 2, 1/2. So that's 1/2 lambda minus 1. So in terms of x and y, so we get a solution that x and y, that vector is 1/2 lambda minus 1 and second coordinate lambda. This is a parametrization of the line, and the parametrization of all the solutions. Parametrization of the solutions. So you plug in any value of lambda into this expression, and you're going to get a solution. In other words, a point on the line. We do recognize here a kind of a parametric equation for the line, and I remind you that we can rewrite this by taking the lambdas out. So we could write this as lambda times 1/2 1 plus the vector minus 1 0. And what does that tell us? That means it's a line through the point minus 1 0 in the direction 1/2 1. Does that make sense? There's the point minus 1 0, and it has direction 1/2 1. 1/2 over, 1 up. So there's a direction vector for the line. Okay, so in this case, there's an unbounded number of solutions. So there's three possibilities that we found. We found an unbounded number of solutions. That was one case. Over here, we found that there was no solution in that case. And in the first example, there was a unique solution. Okay. So these are the three possibilities that basically occur over and over again in the subject. Right? So as we proceed to higher dimensions, it's going to be the same story in that a system of linear equations, okay, so I'll write this, we'll see that any system of linear equations has either a unique solution or no solution or an unbounded, or some people like to say an infinite number of solutions. I'll write that down reluctantly. An infinite number of solutions. I'm not a big fan of infinite sets. Okay, great. So one of the kind of key drivers of linear algebra is to find a technology that will deal with the big system of linear equations and determine whether we either have a unique solution or we have no solution or we have an unbounded or infinite number of solutions. Okay, and of course, if there are solutions, we would then like to know what they are. So if there's a unique solution, well, we'd like to know what it is. If there's no solution, there's nothing to say. But if there's an unbounded or an infinite number of solutions, there's also something to say. We can attempt to describe all the solutions in, in the kind of fashion that I was doing up here. Okay, that's a way of describing solutions in terms of parameters. So here we might have some parameters to describe the solutions. Okay, so now to go further, what we want to do is we want to go to 3 dimensions. Okay, in 3D, we're working in, let me use x1, x2, x3, a little bit more sophisticated, all right? So we have 3 axes, x1, x2, x3. And we might imagine that we have a number of different equations. And so I need to remind you a little bit about what linear equations represent in 3-dimensional space. So for example, suppose that we have the equations, now it's going to be in terms of x1, x2, and x3. So x1 minus x2 plus x3 equals, say, 1. And maybe 2x1 minus x2 equals 3. And maybe x1 minus 2x2 plus 2x3 equals minus 2. Okay. So now we have 3 equations in 3 unknowns, and we would like to understand what the solutions are. So we want to describe the points x1, x2, x3 that satisfy all 3 of the equations. Now I need to remind you, okay, recall that a single linear equation, like, say, x1 minus x2 plus x3 equals 1, represents a plane in 3-dimensional space. Okay, that's crucially important. And this particular plane, so how could we sort of describe that? Well, one easy way is to look at the x1, x2, and x3 intercepts. So when x2 and x3 are 0, then x1 has to be 1. So if there's 1, then that would be a point on the plane. If x1 and x3 are 0, then x2 would have to be minus 1. So we'd let's put some scale here. Okay, so there's minus 1, so that would be another point on the plane. And when x1 and x2 are 0, then x3 is 1, so that would be another point on the plane. So altogether, the plane ends up being the plane that passes through these 3 points. Okay, I might sort of draw it like that, but it actually extends in this 2-dimensional fashion. So it's a plane in 3-dimensional space. Okay, now it's a little bit onerous in general, to draw all the planes involved and try to sort of see the intersection point. Here in 2 dimensions, it's pretty easy because we have a lot of familiarity and we can graph things. And we can say, aha, there's a unique point of intersection. We can see that geometrically. Now we could also do that in here, but it would be a little bit, more involved. But happily, we don't really have to draw an accurate diagram, because we're not determining the solutions geometrically, we're determining them algebraically. Okay, we're solving this system. So let's see if we can do that and see what we get. Okay, so we'll give these equations some names. Let's say that's equation 1, equation 2, and equation 3. Okay, so let's see what happens. Okay, so let's take equation, we're going to replace these equations. So let's take equation 2 minus 2 times equation 1. Okay, I'm going to write that over here. Equation 2 minus 2 times equation 1 for the purposes of removing x1. Okay, removing x1. So when we do that, we're going to get 0x1. Okay, and then how many x2s? Well, minus x2 minus 2 times minus x2. So that's minus x2 plus 2x2. So for a total of x2. And then when we take equation 2 minus 2 times equation 1, the x3 component will be minus 2x3. And on the right-hand side, we're going to get 3 minus 2 times 1, which is 1. Okay, so that's good. We've eliminated x1 from the first 2 equations. And now what we're going to do is we're going to eliminate x1 from the first and the third equations. We're going to take equation 3 and just subtract equation 1. Okay. What I'm doing here is I'm taking this value and this value, and I'm subtracting to get rid of the x1s from equation 1 and 3. Okay, what happens there? Let's see if we can do that. Okay, so we're going to get 0x1 as before. So equation 3 minus equation 2. So altogether there'll be minus x2. And 2x3 minus x3 will be a single x3, so plus x3. And on the right-hand side, we'll get minus 2 minus 1, so a total of minus 3. So now we're, could forget about the original equations. Now we have 2 more equations. Well, let's call them, say, 4 and 5. Now these are 2 equations, but only in x2 and x3. Okay, so we've reduced the problem from 3 equations in 3 variables to 2 equations in 2 variables. Okay, we've done that by getting rid of the first variable by taking appropriate linear combinations. So now we're in a position as we were before. Now we want to reduce by eliminating 1 more variable, let's say x2. How could we eliminate x2? We could take equation 5 and we could just add equation 4. Okay, so that's going to be 0x2 minus x3 equals, sum of those ones is minus 2, from which we deduce that x3 equals 2. And then we plug that back in, let's say, into equation 4 to get x2 minus 2 times 2 equals 1. So therefore x2 equals 1 plus 4, which would be 5. Okay, now we've got x3 and x2. Now we can sub both of those back into one of the original equations. Let's say equation 1. I'll remind you what that was. It was x1 minus x2 plus x3 equals 1. I'll write that down again. x1 minus x2 plus x3 equals 1. So we're substituting these values into there. So we get x1 minus 5 plus 2 equals 1. And so x1 equals minus 3 altogether, 4, I guess. x1 equals 4. So the solution is unique. We get a unique solution. Unique solution, which is x1, x2, x3 equals the point 4, 5, and 2. 4, 5, and 2. Did we do that right? I mean, there's some arithmetic involved here. Let's check. Let's go back to the original equation. So 4, 5, 2. So if I look at the second equation, okay, if I plug in 4, 5, 2, I'm going to get 8 minus 5. That is 3. That works. If I plug into the third equation, it's 4, 5, 2. So 4 minus 10 plus 4 is indeed minus 2. So that works as well. And for the first equation, 4 minus 5 plus 2, that is indeed 1. So yes, that point that we found really does lie on all 3 planes. Okay, where is this point? 4, 5, what do we say? 4, 5, 2. Okay, 4, 5, 2. So it'll be a point on this diagram. It'll be over 4 in this x1 direction, so maybe around here, and then about 5 in this direction, and 5 in the, so maybe that over here, okay, and 2 in the x3 direction, so up here. So let's we have to go here, and then over about here, and then up here like this. So this is sort of the point that we're going to get. Maybe the point that we're going to get. So these 3 planes, whatever they look like, they're going to intersect in one point. Okay, so here's one plane. Here's another plane. Okay. So if I intersect 2 planes, okay, I'm going to get a line. Okay, the intersection of 2 planes is generally a line, unless the planes are parallel, in which case there's no intersection, or they're parallel and they're coinciding, in which case, well, there's a whole plane of points. So these are the 3 possibilities. Just 2 planes. If they meet like this, we get a line of intersection. If they're like this, they're parallel, there's 0 intersection. And if they coincide, well, then there's an unbounded number of solutions, namely every point on that plane. Okay, so what happens if we have 3 planes? So maybe those 2, okay? And then there's a third one, like that one, okay? What's the common intersection going to be? Well, any 2 of them intersect on a line. So just these 2, there's a line of intersection. And then this plane is going to meet that line in at most 1 point. So in this case, it'll be that point right there. Right? So these 3 planes typically meet in 1 point. And that's what's happening in this example that I've just shown you. But that's not the only possibility, right? There's other things that could happen. For example, geometrically, we can have 2 planes that meet in a line like this. And then we can have a third plane just judiciously poised like this, so that it also passes through that common line of intersection. Okay? So in that case, then the common meet of those 3 planes would be a line. That's another possibility. Another possibility is that these 2 planes meet in an unbounded number of points. And then this third plane also happens to coincide with the first 2, so that all 3 planes are basically the same. Well, in that case, the common solutions will be a plane of points, still an unbounded number, but a plane of points. And then there's one more possibility that you get by having 3 parallel planes, like this one here at this level, this one a little bit like that parallel, and this one like this parallel, okay? Then those 3 planes are all parallel, and there's no intersection. Another way that no intersection can happen is the following. We could have the first 2 meet at a line like this. Okay, so there's the meet of those first 2. And then the third plane just manages to miss that line. How does it do that? By having that same direction vector as one of its direction vectors. Okay, so there's actually quite a lot of possibilities geometrically. So I'll summarize that by saying that geometrically, 3 planes in 3D can, okay, there's various possibilities. First of all, they can meet in a single point, as in the example. Or they can meet in a line. Okay, maybe something like this. There's one, and there's another plane, and they meet in this line right here. That's the line of intersection. And then there's a third plane, maybe like this, which also meets in that red line. So that red line is the meet of these three planes. And what are the other possibilities we said? Well, they could also meet in a plane. Or they could have no common intersection. Okay. So in terms of numbers of solution, this would be a unique solution. This first one, unique solution. And then these two, whether they meet in a line or a plane, that would be an unbounded number of solutions. And this other possibility, say this one here, that would be no solution. So this is really representative of what happens with higher dimensions. If we have more variables, we have more equations in our system, still the same kind of phenomena is going to happen as is happening here in these three-dimensional examples that I've worked out one, and I've sort of shown you geometrically some other possibilities. So typically, we're going to have to do some analysis, right? We're going to have to investigate to see which of these various possibilities arise, and then to describe the solutions. If there's a line of solutions, we want to describe that line. If there's a plane of solutions, we want to describe that plane of solutions. If there's a single point, of course, we want to obtain that point. Okay. So what we've done today is we've outlined a very broad program for solving systems of linear equations. And we're going to develop technology to be able to do that systematically. So we want to transcend sort of high school methods that I've been showing you today and adopt more matrix-oriented methods that will very systematically show us which of these various possibilities are happening and actually give us a good way of describing all the solutions for a given system of linear equations. So I'll see you next time.